Welcome to the second lecture of Module 5, Residue Integration. In this lecture, we will look at singularities and zeros of complex functions, residue formula, and finally, the residue theorem from complex analysis. A function f of z is singular or has a singularity at a point z equal to z0 if f of z is not analytic at z equal to z0. If there are no other singularities in the neighborhood of the singularity z0, then z0 is isolated. Otherwise, it's called non-isolated singularity. For example, tan z has an isolated singularity at plus or minus pi by 2, plus or minus 3 pi by 2, and so on. But tan of 1 by z has a non-isolated singularity at z equal to 0. Isolated singularities of a complex function can be classified by its Lorentz series. If f of z has a singularity at z0, then we can form a Lorentz series expansion of f of z centered at z0. If this Lorentz series expansion does not have any negative power terms, z0 is a removable singularity. So for example, if we take the function sin z by z, this function has a singularity at z equal to 0. But if we take its Lorentz series expansion, there are no negative power terms. So for sin z by z, z equal to 0 is a removable singularity. If there are infinitely many negative power terms in the Lorentz series expansion of f of z centered at z0, z0 is an essential singularity. So this time, let's take the function e raised to 1 by z. This function also has a singularity at z equal to 0. But if we look at the Lorentz series expansion, there are infinitely many negative power terms. So z equal to 0 is an essential singularity for f of z equal to e raised to 1 by z. The last classification is pole type singularities. If the Lorentz series has a finite number of negative power terms, z0 is a pole. The highest negative power in the Lorentz series will give us the order of that pole. For example, if we take the function f of z equal to sin z by z raised to 5, this function has a singularity at z equal to 0. Its Lorentz series expansion centered at 0 is 1 by z raised to 4 minus 1 by 3 factorial z square plus 1 by factorial minus and so on. There are only finitely many negative power terms, so z equal to 0 is a pole. The highest negative power in this Lorentz series is 4, so z equal to 0 is a pole of order 4. Another example, f of z equal to 1 by z times z minus 2 raised to 5. 0 and 2 are both poles for this function, but 0 is a pole of order 1 or a simple pole, and z equal to 2 is a pole of order 5. Next, we will look at zeros of analytic functions. A zero of an analytic function f of z is a point z equal to z0 such that f of z0 equal to 0. A zero has order n if f of z0 equal to 0, f dash of z0 equal to 0, and so on until fn minus 1 of z0 equal to 0, but the nth derivative of f at z0 is not equal to 0. For example, take the function f of z equal to sine of z square. Z equal to 0 is a zero of this function. Now if we look at these derivatives, at the derivatives of f of z at 0, we see that the first order derivative of f of z at 0 is 0, but the second order derivative is not equal to 0. Therefore, z equal to 0 is a 0 of order 2 for sine of z square. Another example, f of z equal to 1 minus cos z has zeros of order 2 at 0, plus or minus 2 pi and so on. Next, we will go to the method of residue integration. Some real integrals cannot be evaluated easily using usual integration methods. But with complex integration, we can evaluate such real integrals easily. And the method we are going to follow is called residue integration. Let f of z be singular at z0 but otherwise analytic. Then f of z has a Lorentz series centered at z0 given by f of z equal to sigma n equal to 0 to infinity a n z minus z0 raised to n plus b1 by z minus z0 plus b2 by z minus z0 the whole square and so on. In this Lorentz series, the term b1, the coefficient of 1 by z minus z0, is called the residue of f of z at z equal to z0. It is denoted by b1 equal to residue at z equal to z0 f of z. Now to the residue integration method. Let f of z be singular at z0 but otherwise analytic. Let C be a simple closed path that contains z equal to z0 in its interior but no other singular points. Then integral over C f of z dz is equal to 2 pi I d1, where the integral is taken clockwise, anti-clockwise. For example, evaluate integral over mod z equal to 1 by 2 e raised to 1 by z dz. The function which we are integrating, e raised to 1 by z, has a singularity at z equal to 0. Z equal to 0 is inside mod z equal to 1 by 2, so we can apply the above result. The Lorentz series of e raised to 1 by z centered at z equal to 0 is e raised to 1 by z equal to 1 plus 1 by 1 factorial z plus 1 by 2 factorial z square and so on. From here, we can see that the residue of e raised to 1 by z at z equal to 0 is 1 by 1 factorial or 1. So integral over mod z equal to half e raised to 1 by z dz is 2 pi I times 1, that's 2 pi I. Finding residue from the Lorentz series each time is a lengthy method, but when the singularity is a pole, we can evaluate residue using the below formulas. For a simple pole, we have two methods for evaluating the residue. If z0 is a simple pole of f of z, residue at z equal to z0 of f of z is equal to limit z tends to z0, z minus z0 times f of z. Otherwise, if f of z is in the form p of z by q of z, where p of z0 is not equal to 0 and q has a simple 0 at z0, then f has a simple pole at z0. In this case, residue of f of z at z equal to z0 is p of z0 divided by q dash of z0. Example, find the residue at z equal to I of f of z equal to 9z plus I divided by z cube plus z. If we factorize the denominator, f of z is 9z plus I divided by z times z plus I times z minus I. F has a simple pole at z equal to I. If we use the first method, then the residue is equal to limit z tends to I, z minus I times f of z. Evaluating the limit, this residue is equal to minus 5i. We can also evaluate this residue using the second method. Residue at z equal to I of this function is equal to 9z plus I by 3z square plus 1 evaluated at z equal to I, which is again minus 5i. If on the other hand, we have a pole of order m, then the residue is given by the formula 1 by m minus 1 factorial limit z tends to z0, m minus 1 derivative of z minus z0 raised to m f of z. For example, find the residue of f of z at z equal to 1, where f of z is 50z divided by z cube plus 2z square minus 7z plus 4. Again, if we factorize the denominator, f of z is 50z divided by z plus 4 times z minus 1 the whole square. This function has a pole of order 2 at z equal to 1. So if we apply the residue formula, residue of f of z at z equal to 1 is equal to limit z tends to 1 d by dz of z minus 1 the whole square f of z, which is limit z tends to 1 d by dz of 50z divided by z plus 4, and this is equal to 8. Next, we go to the Cauchy residue theorem. Let f of z be analytic inside a simple closed path C and on C, except for finitely many singular points z1, z2, etc. up to zn inside C. Then the integral of f of z taken anti-clockwise around C is equal to 2 pi I times the sum of the residues of f of z at these singularities. That is, integral over C f of z dz equal to 2 pi I times sigma j equal to 1 to n residue at z equal to zj of f of z. Next, we have the applications of Cauchy residue theorem. First, we will evaluate definite integrals using residue theorem. Evaluate the integral over C 4 minus 3z by z square minus z anti-clockwise around the given path. First one, mod z equal to 2. Second one, mod z equal to 1 by 2. Third one, mod z minus 1 equal to 1 by 2. And finally, modulus of z minus 2 equal to 1 by 2. The function which is to be integrated has singularities at 0 and 1. These are both simple poles, so we can evaluate the residues at these singularities. The residue at z equal to 0 of 4 minus 3z by z times z minus 1 is minus 4. And the residue at 1 is equal to 1. Now let's evaluate the integral over each path. In the first case, we have mod z equal to 2. For this path, both singularities are inside. So by residue theorem, this integral is equal to 2 pi I times residue at 0 plus residue at 1. That's minus 6 pi I. For the second part, we have the contour mod z equal to 1 by 2. But for this contour, only z equal to 0 is inside. So by the residue theorem, this integral is equal to 2 pi I times the residue at 0. That's equal to minus 8 pi I. For the third contour, modulus of z minus 1 equal to 1 by 2, only z equal to 1 is inside. So this integral is equal to 2 pi I times residue at 1. The value of this integral is 2 pi I. For the final contour, mod z minus 2 equal to 1 by 2, neither of the singularities are inside, so by Cauchy's theorem, the value of this integral is 0. Next, evaluate the integral mod z equal to 3 by 2 tan z by z square minus 1. The function which is to be integrated, we can rewrite it as sin z by z plus 1 times z minus 1 cos z. The singularities of this function are at 1, minus 1 and 2n plus 1 pi by 2. But of all these singularities, only 1 and minus 1 are inside the contour. So by residue theorem, the value of this integral is equal to 2 pi I times residue at 1 plus residue at minus 1. That's equal to 2 pi I tan 1.